Okay, ladies and gents. Okay, ladies and gents. You know the topic for today is vectors. Vectors. All right. So hurry up. Draw. Draw this off. You can draw it on a graph paper, or you can draw it in a notebook. All right. So most of you should be done drawing this by now. If you're done drawing, type the word "done" in the chat. Or as soon as you're done drawing, type the word "done" in the chat. So let's Ayana, Taja Marie, Lauren. So that's 4 persons. I just need to see a few more persons. All right, Alexia is done. And so earlier I had sent a link for you guys to watch, a YouTube video link for you guys to watch. Marie Car is done. So most of you guys would have watched that video and you'd have made some notes. I also sent a second link for those who were finished early with the first one. So some persons have started watching the second link for vectors. Waiting for 1, 2, 3, 4, 5, 6. I'm waiting for 4 more persons to say they are done drawing this right here, whether on graph paper or in their notebook. So Ime and Amari, Mr. Drummond, Buckley, and Kelia. All right, ladies and gents. So some of you might want to do a screenshot right now because I'm going to zoom out a little bit. So Chelsea, Badley, Donaldson, persons are finishing up. Some persons might want to do a screenshot right now so you can finish up the drawing because I'm going to zoom out. Well, it's finished drawing though. All right, it's a recent finished drawing there. So approximately half of the class done drawing. And that is who respond. Gonna zoom out a little bit now. So I imagine most persons say Akila. Akila, good morning. Big up yourself, miss. I hear that yesterday was your birthday.
Yes, sir,
Akila,
it was.
It was. Big up yourself. So that was April 19. How old are you
Yes,
now, Akila?
17.
There. 17 years old. Congrats, man. Congrats. Big up yourself. And I wish you so many more years to come. Big up yourself, Akila. Happy birthday. And there was another girl who came to math class yesterday face to face. It was her birthday as well. Yeah. All right, guys. So I'm going to zoom out now. Guys, it's always a blessing to see another birthday, you know? Yeah, man. Wish you guys long life. Long, happy life. With good health, strength, and some money to facilitate the things that you so desire. Wish you to have enough of all that you need, all that you want. All right, ladies and gents. Vectors. Vectors, vectors, vectors. Vectors, vectors, vectors. Now, What is a vector quantity? Now, all right. So the physics students, if you're a physics student, type the word physics in the chat. Let me see how many physics students we have in here. Because the physics students, they're familiar with the term vector, and they know the difference between a vector quantity and a scalar quantity. There's only one physics student. So, ladies and gents, there's a difference between a vector quantity and a scalar quantity. So, for instance, you have, let me use mass. Mass. You're looking at me right now, right? This is my body. This is me. You're looking at my mass. You're looking at my mass. All right? This is me, mass. All right? Now, wherever I go, this is my body. This is my body. This is my mass. So whether I'm here or whether I'm in a pool or in the sea, right? This is my mass. Whether I'm on the moon or Mars or Jupiter, this is my mass, right? However, there is something that changes. My mass doesn't change, but there's something that changes when I'm here to when I'm in the pool, or when I'm on the moon, or when I'm on Mars, or floating on outer space. What changes, ladies and gents? Type it in the chat. What changes? So my mass doesn't change, but what changes? Sitaja Marie said first here, weight. So mass would be a scalar quantity, just as magnitude. A scalar quantity just has magnitude. And by magnitude, we just mean size. All right, so I have a size. I have a size, a magnitude. All right. Weight considers direction. Weight considers direction because weight takes into account a gravitational pull, and gravitational pull has a direction. So the gravity is pulling me down to the earth right now. So it's pulling me. So my weight takes into consideration that downward pull. All right. But mass, it doesn't consider that direction. It only considers the fact that it has a size, while weight has size and direction. All right. So weight is a vector quantity, while mass is a scalar quantity. As you guys would know, in the pool, you can lift up somebody who on land you can't lift them up, but in the pool you can lift them up or them feel lighter, right? Because other forces are acting in the pool. You understand? You can walk here, but in space you float, right? There's nothing pulling you really, all right? So yeah, your weight changes depending on the amount of gravity. All right, so that is, you have scalar quantities and you have vector quantities. All right, I'm going to write something on the board here, make some notes. I'm going to write it down here at the bottom. So we're dealing with vectors today, ladies and gents. Vector quantities have one, magnitude. Another word for magnitude is size. In this case, we're going to be talking about length. So in this case, we're talking about length. All right, length. So it has magnitude, that's first. And secondly, it has direction, which is actually what we look at most in this topic. What we look at most in this topic is the direction. All right, so vector quantities have magnitude and they have direction. And mostly what we actually focus on is direction. Write that down for me, please. All right, ladies and gents. For each of the following vectors, write the matrix T that represents their translation. And word it like this for a reason. We're going to be looking at translation differently. But anyways, for each of the following vectors, write the matrix T that represents their translation. And the first matrix I'm going to ask you to look at, the first vector is the vector ED. So you're going from E to D. So ladies and gents, that arrow above, as you can say, a lot of things with vectors go without saying. You kind of just pick up what it is saying without me actually saying it. You see that arrow and you figure that, oh, you're going from E to D, right? Now, remember you guys watched a video earlier, a YouTube video. So you have an idea of what is what I'm asking you. All right, ladies and gents. So what's the answer? Going from E to D. All right, so let's do this. Let's do this, ladies and gents. So we're going from E to D. E to D. Vectors. There's one rule that you need to know. In moving from one place to the next, from one position to the next, you have to do a horizontal movement first. You have to do a horizontal movement first, and then you do a vertical movement. All right, and then we're going to write it like this. So the amount of horizontal steps we take we're going to put it up here. And the amount of vertical steps we take, we're going to put it right here. So X and Y. That is how we're going to write it, ladies and gents. All right, so we're going to go from E to D. Now you tell me, are we going to go, are we going to go down then across? No, we can't go down then across. We just said the rule. The first thing you need to do is what? Horizontal movement. So we have to go across and then go down to reach D. All right, now how many steps across would we have to take? So we're at 2, right? And where's D? Right here. It's under 4. So from 2 to 4, so you have to go 1, 2 steps to the right, right? And then we want to go from E is at -1 and D is at -5. So how many steps would we take to go from -1 to -5? So let's go down. So first we went 1, 2 to the right, and then it's gonna be 1, 2, 3, 4 steps down. So 2 to the right and 4 steps down. All right. So let's see, 2 to the right and 4 steps down. Ladies and gents, how do I write 4 steps down? Do I just put 4 right there like that? Is this correct, ladies and gents? Say that again.
-4 for the
Negative. And see some persons typing in the chat there. -4 because we're going down. So when we're going down, we put negative, but if we were going up, we would leave it as positive. Likewise, I know people, you guys put it together already. Going right, so in moving horizontal to the right, this 2 is positive. However, if we're moving left, you're right, it would be negative if we're moving left. So persons would just know that. All right, so ladies and gents, there you have that, see? So you could just look at the graph and know that, oh, it's 2 to the right and 4 down. So this tells you how to go from E to D. So if you are a person at E and you say, hey, how do I get to D? Yo, John Star, I'm at E right now. How do I get to D? So somebody's going to say, hey, the direction. So they are giving out direction. See? They're going to say 2 to the right, 4 down. So that's 2, -4. So they are giving direction. So it's the direction. That's a vector. All right. Another way we could look at this, hold on there. Another way we could do this. So E to D is equal to, and don't write anything as yet. So E to D is equal to D minus E. Don't write anything as yet. So D. What are the coordinates of D? 4, -5, don't it? 4, -5. All right, so I'm going to write it like this. 4, -5 minus E. What are the coordinates of E, ladies and gents? 2, -1. Okay, I'm going to write it like this. 2, -1. Ladies and gents, don't write anything as yet. A hummingbird just flew in and flew out. Anyways, so check that out. And then I'm gonna do this. Zine, hold on. So E to D is therefore equal to, guys, what is 4 minus 2? You get 2. And what is -5 minus -1? Well, -5 minus -1, that's -5 plus 1. So that's -4. Don't write anything as yet. So ladies and gents, this is a way we could work this out. This is a way we could calculate this. But hold on. So vector ED is equal to D minus E. All right, let me show you guys a thing. This is the vector ED. We're going from E to D. So vector ED is this straight line here. So somebody comes to you, hey, how do we get to D coming from E? And you say, well, it is 2 to the right, 4 down. That's the vector. See? I want to show you guys something now. I'm going to use this green marker right here. Guys, the center of this Cartesian plane, you know what it is called right here in the center right here? What is that called? What is this location called? The origin. All right. The person's typing it in the chat there. The origin. You see that O? All right. Guys, I'm going to move from the origin to E. From the origin to E. If I wanted to go from the origin to E, ladies and gents, which is what I just did, in going from the origin to E, how many places, what would be the matrix for this vector? I moved to the right and then I moved down. How many places to the right did I move? I moved 2 places to the right and then how many places down? 1 place down. So that's 2, -1. Ladies and gents, you notice that it coincides with the coordinates of E. But then it actually makes sense. It makes sense that it would coincide with the coordinates of E. Why does it make sense? Because, ladies and gents, the coordinates of every point is always measured starting from the origin. So, for instance, guys, if you're at O and want to go to A, how would you get there? Well, horizontal 2, vertical 5. So it's 2, 5. But that is how we end up writing the coordinates of a point anyways. We always go horizontal and then vertical. So this matrix, once you're coming from the origin, ladies and gents, to the point, this right here, this vertical, this column matrix, T, from O to D, it is going to coincide with what D is. So for instance, the D here, you want to go from O to D, because I know that some persons were wondering, why I wrote this vertically. And you're like, sir, this E is a point. And for the coordinates of a point, you shouldn't write it vertically like that. That's why I did say, don't write anything at all. Because yeah, you're right. It's coordinates of a point. I should not just write it vertically like that. Coordinates of a point is written like this with a comma between, right? But what I was actually writing it is as a vector. So I wasn't going to leave it as E. I'm going to write it as O to E, right? Which is what you see right here. So O to E, O to E is 2, -1. And O to D coincides with the coordinates of the point. Coincides with the coordinates of the point as well, because we are coming from O. And so we have this here, ladies and gents. And so you have that there, ladies and gents. So we have O to E, O to D. So ED, ladies and gents, is equal to O to D minus O to E. And it actually works out. And here we have a formula that we need to know. And for some persons, it looks kind of weird, like, sir, So, sir, you're telling me that this vector ED is equal to vector OD minus vector OE. So this vector ED is equal to, if you should subtract those 2 vectors, sir. Really? How comes? Not really see it. I know that many of you guys will just swat this formula, you know. You can go ahead and swat it, but actually it makes sense. And I'm going to show you that it makes sense. I am going to show you that it makes sense. Write this down, ladies and gents. By the way, ladies and gents, remember, you know, pay attention to my explanations first and then write down. So follow the reasoning first. Some of you probably done right already, but you weren't really following the reasoning, which is not the smart way to do things. Follow the reasoning first. You know you'll get time to write down. So ladies and gents, vector ED is equal to vector OD minus vector OE. Know this formula. And notice that this letter, that the last letter comes first right here. So vector ED is equal to vector OD minus vector OE. So it's like them reverse the thing. And you're going to see that it makes sense. You're going to see that it makes sense. I'm going to prove to you that this vector makes sense. This formula, sorry, makes sense. So notice that we got about the same thing. See? So we get the answer correct. It is good. All right. So proof that the formula makes sense. All right. Now follow me. This formula right here. Proof that it makes sense. Now follow me. I'm going to start over by writing it as it is. Vector ED is equal to vector OD minus vector OE. See how that looks? All right. So in this state, it don't really look like it makes as much sense. However, this vector OE right here, suppose I should bring it over there. I'm going to bring it over here, so to the left. This is a negative OE. When it goes over to the left, what shall it become? It shall become positive, right? So when it goes over there, ladies and gents, let me just adjust this. We're going to end up having vector ED plus vector OE is equal to vector OD. And then you're going to now look back at the graph to see if it actually makes sense. So you look and you say, wait a minute. All right, sir, you're now saying then that vector ED, which is here, plus vector OE, which is up here, when you add those two vectors, you'll get the vector O to D. And I'm going to say yes. And for you, it start make sense. It start look like, yeah, it makes sense, sir. Because O to D, because you start at O, you end up at D. And a while ago, you say, is these two vectors. So E to D and O to E. Yeah, it makes sense. But for some of you, you're still not fully seeing it. And ladies and gents, let me just tell you, we're not talking about now the length of the line. So when some of you guys are looking and you're saying, sir, what you're trying to say? You're trying to say, if you should add the length from O to E, and if you should add the length of ED to the length of O to E, those two lengths are the same as the length O to D. And I'm going to say, no, man, no, it's not the lengths I'm talking about, man. It's not the length. I'm talking about the path. I'm talking about the path. Path to walk. If me and you, all right, let me show you a vibe. I'm going to switch these around so that you see it even better. So, this I'm going to bring it over here, and the ED right here, I'm going to bring it right there. So I'm going to write it this way now. So if you should walk from O to E, so it's the path. If you walk the path from O to E, and then you walk the path from E to D, it would be the same as if you're a friend. You're going to end up the same place as if your friend should walk straight from O to D. And when it is written like this, most people are like, okay, sir, for real, it definitely makes sense now. Like this formula now makes sense because at the end of the day, the two, let me put this up here. At the end of the day, so this formula, you need to know formula. Formula. This formula, yeah, you need to know. It's this. So this is when it is written like this, it makes sense to you because you can see it from O to E plus E to D is the same as O to D. When it's written like this, it makes more sense to you guys. So when it's written like this, it don't make as much sense. But this is the formula. This is what you need to know because this is how enough time the question asks. So you get a vector ED, and you have to go know say ED, vector ED is equal to vector OD minus vector OE. You understand what I'm saying? You have to go know this formula. But I went through this to show you that the formula makes sense. So it's like, oh, the formula makes sense. So it's like that, you know? Oh, the formula makes sense. Guys, I'm giving you 1 minute to write that off. Giving you guys 1 minute to write this off. Right, quickly, please. Oh, really? That's how you learned it as? Okay. All right, ladies and gents, there's something else that I have to point out to you guys. Just that terminology. All right. So vectors that start at the origin, vectors that start at the origin. So like OD and so look, OD and OE, those two vectors, any vector that starts at the origin, it has a special name. Do you guys know what that special name is? Type it in the chat if you do. Vectors that start at the origin have a special name. What is that special name? Type it in the chat. See persons typing it in the chat there, ladies and gents, and they are correct. They are called position vectors. And it actually is a good name. It makes sense. That name makes sense. They are called position vectors. Do you think is a sensible name? Does the name make sense to you? Vectors that start from the origin are called position vectors. And let me tell you why to me is a very good name. It's an applicable name. It's because when you check it, all right, the vector, what is the vector OD? It is 4, -5, which coincides with the position of D. It coincides with the position of D, which we already established. That makes sense because coordinates of every point, the coordinates of every location, the coordinates of every position, yeah, you see that? The coordinates of every position, they are all in reference to the origin. They're all in reference to the origin. They all start from the origin. So the vector being called a position vector, it makes sense because it's just the vector itself is going to be equal to the coordinates of the position, the coordinates of the location, the coordinates of the point. You understand? It's beautiful, man. Vectors is beautiful, man. Come on. So, ladies and gents, make a note of that. Position vectors. You wrote it down, right? You never. All right, write it down. Write it down. Write down what are position vectors. Look at somebody. Somebody there right now talking about, sir, is why did say again what are position vector? Hey, write it down, man. Search your memory. Somebody type it in the chat for that person who wasn't paying attention. Type what a position vector. Vectors that start from the origin. Thanks much, Miss Lewis. Big up Alpha. Ladies and gents, moving on. Position vectors. All right, so vector ED is equal to position vector OD minus position vector OE. But I don't necessarily have to say position vector OE because our position vector O anything because from it start with an O, it is a position vector. So it is like being redundant. You guys learned that word in English class, yeah? I learned that term in English class. Anyways, moving on, ladies and gents. Please note that this is a way of giving direction. This is a way of giving the direction of the vector. It is saying where the direction in which the vector is going. It is not telling you how long the vector is or the size of the vector, the magnitude of the vector. It's just giving you a direction. But there's another way to give directions, you know. There's another way, matter of fact, let me write it down. Note briefly, note well. What ND means? Note briefly or note well? Whatever, man. All right? Note NB. Another way to give the direction of a vector is to, and we're talking about in this case, you know, in situations similar to this, is to determine its gradient is to determine its gradient, ladies and gents. Another way to give the direction of a vector is to determine its gradient. So here what? Ladies and gents, go ahead and calculate the gradient. Calculate the gradient of the vector ED for me. Calculate the gradient of the vector ED for me right now. I'm giving you guys 3 minutes to do so. Calculate the gradient of the vector ED. Three minutes to do so. Send the answer in the chat, make everybody see, ladies and gents. So let's just send. Drummond send as well. You can send it, make everybody see. Send your answer, whether it's right or wrong, ladies and gents. What is the answer you guys are getting? Send your answer to the chat. Is -2 correct? Is -2 I see people getting? Giving other persons 20 seconds to finish up. All right, so you all know that the gradient of a line is equal to the change in the y values divided by the change in the x values. Rise over run. The change in the y values divided by the change in the x values. All right? And how many of you will write it then is y2 minus y1 over x2 minus x1. And then you'll go over here, so to the actual graph, and you'll select which one of these points is your first point and which one is your second point. Let's say if you're selected up here, E as your first point. So this x value, this x coordinate right here, you call that x1, and the y coordinate, you call it y1, because this is your first point. This is your second point, so the coordinates are gonna be x2 and y2, and then you plug it in over here, so, all right? You plug in your your y2 value, right? You plug in your y2 value as -5 and minus your y1 value, which is -1, over, you have the x2 value, which is 4, minus your x1 value. You look over there, it is 2. And that gives you -1 plus 1 is -4. And that is over 4 minus 2, which is 2. And so the final answer is -2. Let me come down here so it. Ladies and gents, I want to point out something though, you know. All right. Let me use. In this movement, right? In going from E to D, there was a We shifted in the x value, we shift in the x and then shift in the y, don't it? So this is the shift in the x value. We shifted 2 times in the x value. We changed the x value by 2, and there was a change in the y value by -4. So really and truly, check this out. You guys looking? So which there was a change in the x value by 2 and a change in the y value by -4. So the fact that we know that gradient is equal to change in y divided by change in x automatically would be -4 divided by 2, which is what we have here. So, all right. So see it there, the change in y value divided by the change in the x value is equal to -4 divided by 2. See it there? So what some people did, some of your classmates a while ago, when you see them finish so fast, some of them what they did is they say, wait, but this is the change in the x value, this is the change in the y value. And we're going to find gradient. You just put the change in the y, you just flip it. You know, you put change in y divided by change in x. And you get the answer, -2, you know. But in my mind, I'm thinking as well, suppose you never do this part first, you know. So you'd still have to go right here and look at the coordinates themselves and work it out, you know. But guys, I just wanted to point that out as well. Somebody might want to make a note of that. So I'm going to give persons about another half a minute or a minute so you can make a note of the whole change in y over change in x that you can actually get from the matrix right here. You can make a note of that, giving you guys a minute to do so. And I hope you guys made a note, you know, of what position vectors are. All right. Right here, so I'm on alpha. Vectors that start from the origin. So example, E would be 2, -1. Therefore, vector OE is equal to 2, -1. Like that. So I'll give an example as well. All right, ladies and gents, let's go. I'm gonna rub off over here, so now I will continue with the work. If you need to screenshot, I'll give you 5 seconds to screenshot. 4, 3, 2, 1, 0. So I'm gonna rub off over here now. All right, so remember now, for each of the following vectors, write the matrix T that represents their translation. And so here are the other two that you need to do. So this is so you're gonna do vector BC right now. And you're also gonna do vector HC. Do those two for me right now. Thank you. I expect you to finish it in 3 minutes, tops. So you should have the diagram drawn. But let me just zoom in a little bit back right here. So we want BC and we want HC. Vector BC and vector HC. And I don't know if you guys are able to type the answer in the chat. Type the answer in the chat for me, please, as soon as you get it. And you can type it so that everybody can see your answer. Thank you. Vector BC and vector HC. Thank you. Was somebody saying something just now? Yeah, anybody? All right, cool. Ladies and gents, see some answers coming in. See some answers coming in. Let us see if you saw it go. So from B to C, you know the formula is it's gonna be OC minus OB. All right, and so that is gonna be equal to OC, which is 6,3, minus OB. You just need to look at the coordinates of B because this is a position vector. 2, 1. And you get the answer. 6 minus 2, that is 4. And 3 minus 1, that is 2. And that's your answer. And then HC is going to be equal to, so HC is going to be equal to OC, vector OC, minus vector OH, right? And so that is going to be equal to what are the coordinates of C? Because again, it's a position vector because it starts with O. So you just need to know coordinates of C, which is 6, 3, right? Minus OH. So that's a position vector. So we just need to know the coordinates of H. So that's -2, 1, -2, and -1. So that's going to be equal to, let's see, that's therefore going to be equal to 6 minus -2. So that's going to be 6 plus 2. Sorry. That is 8. Yeah. And then 3 minus -1. 3 minus -1 is 3 plus 1, which is 4. Ladies and gents, I like these two answers. This is 4, 2. So BC is 4, 2. HC is 8, 4. Ladies and gents, anything look like any relation between the two of them? Anything look? Talk to me, ladies and gents. Because this is 4, 2 and this is 8, 4. Tory, no, we couldn't add. We couldn't add. No, man, we couldn't have added. This formula is a subtraction. Remember, we had looked at it earlier, you know? Ladies and gents, you're realizing that one AC is actually similar to BC. It's just that it is twice as big. So if we should if we could factorize, look at me. Where am I? Where am I? Yeah, so quote unquote factorize, ladies and gents. If we could factorize out this 8 and 4 so that this look all right. Watch here, ladies and gents. Zin. Let us say we realize that this can be something multiplied by 4, 2. Guys, if you could factorize out the 2 out of this, put the 2 on the outside right there. So, ladies and gents, 8, 4 is actually equal to 2 times 4, 2. You know, see that? Let me adjust this right here. So, let me adjust that right there. So, ladies and gents, look at that. So 8C, what here now? This is the answer that we got for BC. And essentially, this is the answer that we get for HC. Well, actually, it's 8-4 we got, This is the answer, But I want to show you something. So this is the answer, 8-4. But I rewrite it by, again, quote unquote, factorize. Just for want of a better term, it is quote unquote, what, ladies and gents? Factorize. All right? So that it looks more similar to BC. So what this is saying, ladies and gents, is that HC and BC are actually going in the same direction of 4-2. But it's just that HC is 2 times bigger. HC and BC are going in the same direction, ladies and gents. And what is that direction? The direction is 4-2. But it's just that HC is 2 times bigger. So we're looking at and say this is 4-2 and this is 8-4. Now we say, wait, the thing look like something something. You have to be able to make that. And it's like you connect it and you say, wait. But if I quote unquote factorize out the thing, she said the same thing, man. All right, ladies and gents. So yeah, that is how it is sometimes. Let me rub out. Let me rub out over here. Let me rub out over here. Because this is now interesting. This is interesting. You might want to make a note of what we just observed. As a matter of fact, please do. So get this if we quote unquote factorize. Right? So we get that if we quote unquote factorize. I'm gonna write something about right here. See? I'm gonna write something about right here. I'm gonna help you with your notes right there. If we quote unquote factorize vector HC to a point, we see that HC so vector HC and vector BC are, and I will come up here, so scalar multiples of each other. Scalar multiples of each other, ladies and gents. Let me zoom out a little bit now. You see that they are the scalar multiples of each other. You can zoom back, go straight out now. All right. That is, and guys, an underline scalar multiples. That is, vector HC is twice vector BC or, if I am 2 times taller than somebody, how else we can say? We can say that somebody is what? If I am 2 times taller than somebody, we can say the other way around and say that somebody is, let me see who's paying attention. All right, then see, Livingstone said there is half. So we can either say AC is twice BC, or we can say BC is half vector HC. Anyhow you take it, they are scalar multiples of each other. And guys, you see when two vectors are scalar multiples of each other, it means that they are going in the same direction. Write that down, ladies and gents. When two vectors are scalar multiples of each other, it means they are going in the same direction. It's just that one vector might be longer than the other. Just that one vector might be longer than the other. So ladies and gents, BC and HC, they're actually going in the same direction because you notice, so this is 4, 2, and this is 2 times 4, 2. So they're actually going in the same direction. It's just that HC is 2 times longer. All right? So it's just that HC is 2 times longer. So you have that written down? All right, ladies and gents. I want to point out something else to you. I want to point out something to you guys. I want to reason with you a little bit. I want to reason with you a little bit. Now, follow me, follow me, follow me. Stop the writing. All eyes on me. All eyes on me. Pay attention. Attention, pay. So we have the vector BC and HC. You notice both of the vectors are ending at C. Both of them have C in it, which means they share a location. They do what, ladies and gents? They share a location. There's some point at which the two vectors meet. So HC, BC. At some point, these two vectors meet. But there's something special about these two vectors. They meet at some point because they share a letter. And both vectors have the same slope. They are going in the same direction. They are going in the same what? Direction, meaning they would have the same gradient. So if you should find the gradient of BC, right? If you should find the gradient of BC, so this is change in X, right? Change in X, and this right here is change in Y. And how do you find the gradient? It is change in Y divided by change in X. So what would be the gradient of BC? It would be 2/4, which is a half. Likewise, with HC, then the gradient would be the change in the Y divided by the change in the X. So it would be 4/8, which is a half. So both of them have the same gradient, which we already established that they are going in the same direction. So if they are going in the same direction, it must mean that they have the same gradient. True or false? Make sense? Remember earlier on, I was saying that finding the gradient of a line is another way of saying, of finding the direction of the line, of the vector. So both of them have the same gradient. We already established that both of them going in the same direction because this is 4,2 and this is 4,2. All right? So ladies and gents, if two vectors are going in the same direction and it turns out that two of them share the same point. Now, I want you to follow this reasoning with me. Let us say you have the point. Let us say that we are going to a location W, right there, so. Let's say we are going to this location W. And I am Lance. So I start, this is L. And I go like this. And I say, hey, this is the direction I walk to go to W. So I walk along a vector of whatever, 10, 6 from L to W. That is my gradient, L to W, 10, 6. That is my direction, 10, 6. Now, if somebody is walking from this direction, let us say him name Malcolm, and he's walking in that direction. Can Malcolm be walking? Can he say he's coming from the same direction to reach W? Is he walking in the same direction? No. What about if K is right here, so I'm going. Is K walking in the same direction as L? No, it's not going to be the same direction. It's not the same gradient. It's not the same line. It's not the same. What about this person around here? So, no. Guess what, ladies and gents? There's only one way that somebody can say that they are walking my gradient, my direction. It is that one way is if they're coming from my direction to go to W. If the aim is to end up at W, all right, so just like so B to C and this is H to C, it has something in common. So if the aim is to reach W and there's somebody who is going to say they're coming from my direction, it means that them definitely have to be coming from my direction. So it means that they're probably coming from here or they're coming from here, or they're coming from here or here, but they are coming from somewhere along the path. True or false? It makes sense, no? So, ladies and gents, BC and HC, two of them end up at C, and two of them coming from the same direction. BC and HC, two of them end up at C, and two of them coming from the same direction. They travel the same direction, they have the same gradient. So guess what, ladies and gents? Those two vectors, some fifth formers can tell me then. There's a special name that is given for two vectors that meet at some point. If the two vectors meet at some point, meaning they share a letter. If they share a letter, it means that they meet at some point, don't it? Make sense? Two vectors share a letter and they are going in the same direction, or they are coming from the same direction. There is a special name for those two vectors. Type it in the chat. What is the name for those two vectors? Chitaja Marie said, dear ladies and gents, collinear vectors. Collinear vectors. Ladies and gents, BC and HC, they both share a location, which means they're both gonna meet each other, they're gonna touch each other, and they're coming from the same direction or going in the same direction. Guys, it means that those two vectors, they connect and form a straight line. They connect and form one straight line. They overlap as one line. The overlap, ladies, all right, you don't believe? Watch this. Watch this. I'm gonna show you on the graph. You guys, some of you guys do your graph on graph paper, so yours is gonna look perfect. Use a ruler for me, please, right? Use a ruler and draw the vector BC. Connect BC on your graph paper right now. Connect BC. Should I use a blue marker or black? I'm gonna use a black. Connect BC for me, please. To BC, dear ladies and gents. Zine? Now, connect HC and see what happens. Draw the line HC, especially those of you who have graph paper. Yours is going to end up perfect. Let me do my thing right here. So, see, dear ladies and gents, from H, draw to C. See? I'm going to see. See some overlap? I'm going to see, but you see some overlap? Overlap, ladies and gents, and create one vector. Collinear vectors, ladies and gents. Collinear. When two vectors meet at a point, the two vectors share a point, and they are going in the same direction, those two vectors are called collinear vectors, ladies and gents. Ladies and gents, look at that. Look at what I just wrote down there, ladies and gents. When two vectors are going in the same direction, which means that they are scalar multiple of each other, and they share a point, then those two vectors are called collinear vectors. Let me write out the word vectors, collinear vectors. And you saw it happen for yourself on the graph. Giving you guys 30 more seconds to finish writing this off and absorbing what is being said. So I'm going to zoom out back now, ladies and gents. You can screen grab, screenshot what's needed. But yeah, you guys, you saw it play out over there from B to C and then from H to C. Collinear. Just like that, ladies and gents. All right, so I'm going to rub out some of right here. So guys, we're going to go up to about 1140 thereabout. All right, so yeah, just work with what is what. All right, so I'm going to rub out, yeah. So we learn collinear vectors. I'm going to rub this out, guys. So that's HC, right? Next thing I want you guys to do. Guys, vector EF. Vector EF. That's where we reach now. vector EF. Giving the guys 1 minute to work that out. All right, ladies and gents. What's the answer? Send the answer to the chat for me, please. What's the answer you guys got for this? So it's going to be OF. That's the formula. Minus OE. That's the formula. F. Coordinates of F. -2, -3. Minus the coordinates of E is 2, -1. So we'll get right here, so now. -2 minus 2, that looks like -4 to me. And -3 minus -1, so that's -3 plus 1. That gives us negative. Wait a minute. What? Hey, hey. I'm observing something again. I am observing something again. Anybody notice a little thing right here? So a while ago with this answer. Let's you notice anything, Tasha? Sashne, Reese, notice anything? Drummond, Livingstone, what you notice with this answer compared to the answers above? Compared to BC and HC. Come on, man, see it there. It's just the negative of. It's just the negative of BC. EF is actually equal to the, if you should quote unquote factorize, ladies and gents. If you should quote unquote factorize out and you take out the -1, and you go so -1 into -4 give you about the 4, -1 into the -2 give you about the 2. Ladies and gents, look at them, man. EF is just the negative of BC. Yeah, man. EF turned out in this case to be the negative of BC. EF and BC are scalar multiples of each other, with that scalar multiple being -1. with that scalar multiple, in this case being -1, ladies and gents. And come on, let's see who in here following. Ladies and gents, when two vectors are the scalar multiple of each other, when two vectors are the scalar multiple of each other, what do we know then? What does it mean? When two vectors are the scalar multiples of each other, we just wrote it in our notes about 10 minutes ago or 20 minutes ago.
They're going in the same direction.
It means that they are going in the same direction. Come on, no man. It means that they are going in the same direction. Thanks much, no man. In this particular case, though, EF, BC, guys, are there any common locations? Are there any common points? Yes or no? Do those two vectors share anything, any of their locations in common? No. Right. See people answering in the chat there, no. So they are going in the same direction, but they actually don't share any common points. There's a name for those type of vectors as well. And you guys, you know the name. You know the name. You know the name. Two vectors are two lines that are quote unquote going in the same direction. What is the name for those two lines? Parallel. See it there, Taja? Parallel. And as a matter of fact, wait a minute. If we should draw EF, let's draw EF on this right now. Those of you who have graph paper, draw EF on your graph paper, and yours will look even more perfect. All right? The thing is, all right, so we remember BC is going that direction in an HC as well, yeah? But you see, parallel is not really just about direction by itself. Parallel really mean maintaining the same distance apart from each other as you pass each other, right? So two roads, you can build two roads to be parallel to each other, but the cars are going this direction on that one, and on the other roadway, cars are going in the opposite direction. But still, you'd still say that the cars are driving parallel to each other. The two roads run parallel to each other. You understand what I'm saying? So it's not really just about the direction of traffic, but it's also about maintaining the same distance. All right. And the point is, BC, even though right now the arrow goes so, you can run up and down on it so. Even though the truth is though, if going this way is positive BC, then going the next direction would be negative BC, don't it? But we don't want to get too technical right now. But yeah, these two would be considered parallel. Let's go E to F. Bam. And we're going this direction, But we are considering them to be parallel. All right. We have the idea that they do maintain the same distance apart. They do maintain the same distance apart. All right. This is why I say negative BC, negative BC. So negative BC. So EF would actually be equal to negative BC. It don't equal to BC now because we know BC is actually going in this direction up here. So you're looking at me. So BC is going in this direction up here. So to me, right? So EF don't equal to that, but it would be equal to negative BC, which is going in the opposite direction. It is going in that direction. You see that? So yeah. See that? Guys, you see that? So if going up is positive BC, going in the opposite direction is gonna be negative BC. We already know how them things there work. Anyways. So EF is equal to negative BC. Negative BC goes that direction. Anyways. So let's write some notes about the parallel. EF and BC are scalar multiples of each other. Let me continue writing. However, they do not share a common point. This kind of sound redundant, but anyways, share a common point. Therefore, they are not collinear, but are instead parallel. There you have that. Parallel. Write that down. I'm giving you guys 1 minute. I'm giving you guys 1 minute to finish writing, and then I have 2 more questions for you. So yesterday the classes went 15 minutes, 10 to 15 minutes overboard. I was trying to finish you guys within 10 minutes overboard, but it looked like it will reach 15 minutes over. All right, so we might end at 11:45, but I want to ensure that you guys are on the same level, at the same spot with the classes from yesterday, in which again I did go over the time because I wanted to reach at a particular point in vectors. Guys, I have a question for you. You're supposed to done writing now. Look at this vector OE right here. You have to look at me on the board. Right here, OE, from O to E, and they are from E to D. See? O to E, E to D. They share a common point. Which common point is this? Which point do they share? They share E, O to E, and E to D. If 2 vectors share a common point, does it automatically make the vectors collinear? No, that don't make no sense. Sharing a common point don't automatically make it collinear. It just means that the 2 vectors meet, they touch. What makes 2 vectors collinear is that they share a common point and what else? So they share a common point and what? Let's see if somebody going to type it in the chat. And they are parallel, yeah. So they are going in the same direction. So that if you see that they share a common point and they are going in the same direction, then you'll say that they are collinear. See? Yeah. But if they just share a common point alone, it just means that them touch, don't mean that them necessarily collinear. You understand? And 2 lines can be going in the same direction, but they don't meet. So in that case, those lines are parallel. Now, ladies and gents, all the while since class start, a bare direction we're talking about. Direction, direction, direction. But is direction alone vectors have? Is direction alone vectors have, ladies and gents? No. Vectors also have what is called magnitude. Guys, I'm going to rub out over here. So I have a question now. I have a question. What is the magnitude, or calculate the magnitude of vector ED? Calculate the magnitude of vector ED. Do that for me right now. Do that for me right now. Calculate the magnitude of vector ED. Ladies and gents, do you know how to calculate the magnitude of vector ED? All right, cool. Go ahead, ladies and gents, and calculate the magnitude. Good, ladies and gents. See here, Livingstone. Some persons in here never know how to do it, you know. They just sit down there quiet, even though I say, do you know how to do it? Them sit down there shy. The whole year done and them now still shy. Ladies and gents, magnitude is the same as size, is the same as length. Remember I said that at the beginning of the class, that as it pertains to this topic, magnitude is length. We're talking about the length of the line, ladies and gents. So when I say I want the magnitude of the vector ED, just calculate the length of the line. Just calculate the what? The length of the line. Go ahead and do that. You know the formula to calculate the length of a line. You learn the formula in the topic coordinate geometry. The same time you're learning how to find the gradient of a line and how to find the midpoint of a line. Yeah, same time. You learned how to find the length of a line. So go ahead and do that right now for me, please. So length is equal to the square root of the change in the x values squared plus the change in the y values squared. So the length of vector ED, is therefore going to be equal to, guys, you're getting your answers? Send your answers as you get them. You can write your answer to 1 decimal place. You can write your answer to 1 decimal place, ladies and gents. So the change in x, what was change in x again? See there, it was 2. So that's going to be 2 squared. Plus, what was the change in the y value again? It was -4. So that's going to be -4 squared. So that's going to be equal to square root of 4 plus 16, right? So that's equal to the square root of 20, which is equal to approximately 4.5 units, ladies and gents. So that's the magnitude of vector ED, ladies and gents. Or some people will leave it at the square root of 20, because that is a more perfect answer. Really and truly, 4.5 is an approximation. So, you know, it's really the approximation sign we should use whenever we're rounding off something, you know? Whenever you're rounding off something for real, it's the approximation sign you must use. As it's round it off to 4.5. Really, the answer is 4 point something, 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 never ending. All right, but the perfect answer would actually be square root of 20. Ladies and gents, there you have it. So all three groups are now on the same page, the same level. We're at the same point. Parallel vectors, collinear vectors. We know the direction is given by this column matrix right here, or we can use the gradient. We can consider the gradient of the line for direction, and we know how to find the magnitude. And so this covers most of the basics as it pertains to vectors. Ladies and gents, just pay attention to the WhatsApp group for updates. I would probably love to see you guys actually tomorrow at some point, because remember I sent a multiple choice paper to the group. We will talk about that. Pay attention to the WhatsApp group, pay attention to the WhatsApp group, pay attention to the WhatsApp group. Ladies and gents, there you have it. There you have it. I'll see you guys next time. Pay attention to the WhatsApp group. Ladies and gents, I'm out. Pick up yourselves. It was a good session. Take care, man. Take care, man. Take care, man. Take care, Jade.